In this problem, we are given a truss shown with constant AE, where the modulus of elasticity equals 200 gigapascals and the area of the cross-section is equals 2000 millimeters squared, where it has to find the horizontal deflection at joint B. And to solve this problem, we apply the vertical work method for truss. So first, we need to solve for the forces in each member of the truss. So let's start solving for the reaction at A. That is a pin support, so it has both horizontal and vertical forces. And at the roller at T, it has a force that is perpendicular to the surface. We call this Cy. So taking summation moment at point A equal to 0, considering counterclockwise to be positive, we have 35 kilonewton times the moment arm of 4 meters minus the 84 kilonewton force that will induce a clockwise moment times its moment arm distance of 4 meters, and then plus Cy that would induce a counterclockwise moment times its moment arm distance of 7 meters, all equal to 0. So we have 35 times 4 minus 84 times 4 plus Cy times 7 equal to 0. We have Cy equal to 28 kilonewtons. And as well for Ay, with the summation force vertical equal to 0, we have negative 84 kilonewtons plus 28 kilonewtons from Cy plus Ay equal to 0. Keep solving, we get Ay equal to 56 kilonewtons. And this is all for Ax, with the summation force horizontal, and by inspection, this is equal to 35 kilonewtons. That would resist this horizontal force alone. Next, we did dismember each member of the truss. So start by analyzing at joint A to solve for AD and AB. We have a 35 kilonewton force and a 56 kilonewton force and a force AD. Let's assume tension. And since this is a isosceles right triangle, therefore this angle here should be equal to 45 degrees. And for member AB, let's assume tension. We can take summation force vertical and horizontal to solve for AB and AD. So by taking summation force vertical equal to 0, we have the component of AD. Its vertical component, we multiply this by sine of 45 degrees plus the 56 kilonewton force, all equal to 0. Now solving, we get AD equal to negative 79.1959. Now since the value is negative, therefore AD should be in compression. So the sign here should be negative. Solving for AD again, we get a value equal to 79.19596. And to solve for AB, we take summation force horizontal equal to 0. So we have the 35 kilonewton force going to the right plus AB minus the component of AD that is going towards the left, that is AD cosine of 45 degrees, all equal to 0. Now solving for AD, we have 35 plus AB minus AD that we have solved a while ago times cosine of 45, all equal to 0. We have AB equal to 21 kilonewtons. Since it is positive, therefore our assumed direction for AB was correct. So let's write this down. Let's do this down right here. AD is in compression and AB is in tension. Next, we begin analyzing joint C. To solve for BC and CD, we have CY going upwards, that's 28 kilonewtons, and assuming tension for both numbers, we have CD with a slope of 4 vertical and 3 horizontal. Therefore, this is a 3, 4, 5 right triangle. And then BC. So we can take summation force vertical to solve for CD first. We have 28 kilonewtons plus the vertical component of CD. So we multiply this by sine theta, that is equal to 4 over 5 based from this right triangle, all equal to 0. Solving for CD, we have 28 times CD times 4 over 5, that is all equal to 0. Solving for CD, that is equal to negative 35 kilonewtons, and since it is negative, therefore CD is in compression. Now solving for BC, let's adjust this arrow here. Now solving for BC, we take summation force horizontal equal to 0. We have CD times cosine of theta, that's 3 over 5, minus BC, all equal to 0. So we have CD, that's 35, times 3 over 5, minus BC, equal to 0. So solving, we get BC equal to 21 kilonewtons. And since the sign is positive, therefore, our assumed direction for BC is correct. It is in tension. Now solving for member BD, we consider at point B that has a 84 kilonewton force going downward, and force BC that is in tension, and force AB. So by inspection, BD must be equal to 84 kilonewtons to counter the vertical force going downwards. So BD is in tension. And to solve for the horizontal deflection at joint B, we erase all the actual forces applied to the truss and consider a point load that has a magnitude of 1 applied at point B in the horizontal direction. So let's assume it is going towards the right. Now we solve again for the reaction at each member. So first we need to solve for the reaction first at the support. So let's call this AVX and AVY. And this one here is CVY. So by taking summation moment at point A, by inspection, CVY must be equal to 0. And by taking summation force vertical, by inspection, AVY must be equal to 0. And AVX must be equal to 0 by taking summation force horizontal. AVX must be equal to 1. And it should be going towards the left. Now dismembering the members of the truss, considering at joint A, we have a 1 unit load going towards the left, and force member AB. Since we are considering a vertical truss, let's place a subscript of B to denote a vertical force, and then we have force member AD acting at an angle of 45 degrees. So by taking summation force vertical equal to 0, we can see that ADB must be equal to 0 since it is not resisting any vertical force applied at this joint. And ABV must be equal to 1. So let's list this down here. Next, we consider at joint C. that has no load applied at that point, only force member BC and CD. And by inspection, by taking summation force vertical, this one is equal to 0, and this one here must also be equal to 0 by taking summation force horizontal. So force member BC and CD is a zero force member, or they are zero force members. Next, we proceed analyzing at joint B that has a 1 unit load applied to the right, and force BC that has a magnitude of 0, and force AB that has a value equal to 1 unit. And for BD, since it is resisting no vertical force applied at this joint, therefore this force here must be equal to 0 by inspection. And then after that, once we have our actual and vertical forces, next we will list down the length of each member, AB, and then length AD, BC, CD, and BD. So based from this figure, AB has a length of 4 meters, or in millimeters. To make our dimensions consistent, this is 4,000 millimeters. And AD, that is equal to square root of 4 squared plus 4 squared, that is equal to 4 square root of 2 meters, or in millimeters we multiply this by 1000. And for BC, that is equal to 3000 millimeters. And for CD, that's the square root of 3 squared plus 4 squared, that is equal to 5 meters, or 5000 millimeters. And for BD, that's 4 meters, or 4000 millimeters. Let's simplify this. Then AD, that is equal to 4000 square root of 2 millimeters. Now to solve for the horizontal deflection at joint B, we take the summation of the forces that is actually experienced in that member multiplied by the vertical force experienced in the same member times the length of that member divided by the cross-sectional area times its modulus of elasticity. So beginning with member AB, it has a force equal to 21 kilonewtons in tension, or in newtons that's 21,000, multiplied by the vertical force experience in AB, that's 1 unit, times a length of 4000 millimeters, divided by AE, that is constant, so that's 2000 millimeters squared times 200 gigapascals, or in megapascals, that's 200,000 newton per millimeters. So it adds up to the next member. So AD, that has and the sign here should be negative because it's in compression, times a vertical work of a vertical load of 0. So this entire expression will become 0 due to the factor of this vertical force. Now notice that only AB has a value that is not equal to 0, and the rest of the members will become 0 because of this factor of 0. Now we can solve for the horizontal deflection at B. So we have 21,000 times 4,000 all over 2,000 times 200,000, that is equal to 0.21 millimeters. And this is our final answer.